So let's talk about a mathematical rule that sounds, well, almost silly. It's so obvious. But it turns out to be one of the most powerful tools we have for proving things with absolute, rock-solid certainty. It's called the Pigeonhole Principle, and you're about to see how it uncovers hidden truths in everything from computer science to simple party tricks.
All right, let's just jump right in with a puzzle that sounds completely impossible. I mean, there's no way you could solve this with certainty, right? Well, this is the classic example that really sets the stage for everything we're about to discover.
So, here it is. Just think about that for a second. How on earth could you prove that? You don't know anyone in London. You can't go around counting everyone's hair follicles. It absolutely feels like a trick question, but I promise you it's not. The answer is a definite yes.
Okay, first piece of the puzzle. The population of London is over 9 million people. Now, for our little thought experiment, let's imagine every single one of those peoples is an item we need to sort. Let's call them our pigeons.
And now we need the boxes to sort them into, our pigeonholes. Well, what are we sorting by? The number of hairs on their head. A typical human head has about 150,000 hairs, but to make this proof completely bulletproof, let's use a ridiculously high number. Let's just say, for the sake of argument, that it's physically impossible for a human to have more than 1 million hairs. That gives us 1 million possible categories, or holes, to put people into.
So, let's recap. We have more than 9 million pigeons, that's the people of London, and we have only about 1 million holes, the possible hair counts they can have. The solution to our seemingly impossible hairy problem lies right there in that mismatch.
And that is the Pigeonhole Principle in a nutshell. It's just a simple logical rule. If you have more items than you have containers, it is an absolute certainty that at least one of those containers has to hold more than one item. So with our 9 million people, our M, and only 1 million possible hair counts, our M, at least one of those hair counts must be shared by at least 2 people. It's not a chance, it's not a probability, it's just a logical necessity.
To put it as simply as possible, if you're trying to stuff 10 cats into 9 boxes, one of those boxes is going to have to hold at least 2 cats. That's it. That's the whole idea right there.
Now, this idea has been floating around for a long time. We see references to it as early as 1622. But it was the German mathematician Peter Dirichlet who really formalized it back in 1834. And he called it the drawer principle, which gives you that exact same mental image, right? You've got more shirts than you have drawers to put them in. Something's got to double up.
Okay, so let's really lock this concept down with a couple more classic examples. These will help build your intuition for this surprisingly reliable rule.
Okay, picture this. You've got a sock drawer with only 2 colors of socks. Let's say blue and black. It's pitch black, you can't see a thing. How many socks do you need to pull out to guarantee you have a matching pair? Well, your holes are the 2 colors. The first sock you grab could be blue. The second sock could be black. But the third one, what choice does it have? It has to be either blue or black, which means you are guaranteed to have a pair. 3 socks are pigeons. 2 colors are holes. More pigeons than holes.
Now for a slightly more mind-bending one. In any group of people, at least 2 of them have shaken the exact same number of hands. How can we prove that? The people are our pigeons. The number of hands they could have shaken are the holes. So in a group of, say, n people, the number of handshakes could be 0, all the way up to shaking hands with everyone else, which is n minus 1. But here's the clever bit. Think about it. Is it possible for one person to have shaken 0 hands while another person in that same group shook hands with everybody? No way. Because if someone shook everyone's hand, then nobody could have shaken 0. So those 2 extremes, 0 and n minus 1, can't exist at the same time. This means for n people, there are only n minus 1 possible handshake counts available. We've got more people than possibilities. A match is absolutely guaranteed.
Okay, so this isn't just for fun brain teasers. This principle proves something absolutely fundamental about the technology we use every single day. I'm talking about file compression.
First, a super quick definition. Lossless compression, think zip files, RAR files, that kind of thing, is a way to shrink a file size without losing a single bit of information. You can always get the exact, perfect original file back.
So here's the big question the Pigeonhole Principle can answer with total certainty. Is it possible for an algorithm like zip to always make a file smaller, no matter what file you feed it? Let's frame this with our new favorite tool. Our pigeons are going to be every single possible file of a specific length. Let's call it n bits long. And our holes? That's going to be all possible files that are shorter than n bits. If some magical algorithm could shrink every single file of length n,
It would have to map every one of those pigeons into one of the holes.
So how many pigeons are we talking about? For a file made of n bits, where each bit can be a 0 or a 1, there are 2 to the power of n possible unique files. It's a massive number, but it is a specific, finite number.
And how many holes do we have? Well, if you count up all the possible files of length 0, plus all the files of length 1, and so on, all the way up to n-1, it's a little bit of math, but when you add all those possibilities together, you get a grand total of 2 to the power of n minus 1. And there it is. Do you see it? We have 2 to the n pigeons, but only 2 to the n minus 1 holes. We literally have one more file than we have available shorter spots to put them in. By the pigeonhole principle, it is impossible to give every unique long file its own unique short file. At least 2 original files would have to get crushed into the exact same shorter file. And if that happened, how would you know which one to decompress back to? You couldn't. This proves with certainty that for any lossless compression algorithm, there must be at least one file that doesn't get smaller.
So we know that at least one box has to have more than one item. But what's really cool is that we can get even more specific. The principle has a stronger, more generalized form that can tell us the absolute minimum number of items the most crowded box is guaranteed to hold.
Okay, this is the generalized version. And don't let the symbols freak you out. All it says is, if you have n items and m boxes, you just divide n by m, and that little ceiling bracket just means you always round the answer up to the next whole number. That's it. That number is the guaranteed minimum for the fullest box.
Let's make that really concrete. Say we have 7 players who want to join a tournament with only 4 teams. The players are our pigeons, the teams are our holes. We just calculate 7 divided by 4, which is 1.75. We round that up and we get 2. The principle guarantees with 100% certainty that at least one of those 4 teams will have at least 2 players.
And that's really the big idea here. The pigeonhole principle isn't just some abstract math trick for puzzles. It's a genuine tool for reasoning. It lets us find these points of absolute certainty in systems that otherwise seem really complex or totally random.
You know, I think this quote from an Oxford University textbook just nails it. Delightfully simple and surprisingly powerful. That combination is exactly what makes this idea so cool. It gives us a little foothold of certainty in what can feel like a very chaotic world.
And really, that's the final thought I want to leave you with. From the hairs on our heads to the data on our computers, this one incredibly simple rule forces a kind of order onto the world. And it just makes you wonder, what other profound truths are hiding out there, in plain sight, just waiting for the right simple question to be asked?